So welcome to this webinar. The presentation topic is localization and mapping in autonomous driving vehicles. So my name is Alvin Paulos. I was a MSc student in 2012-2014. Currently, I'm working as a researcher in Center for ICT and Automobile Convergence in Kembuk National University, Daegu, South Korea. So during the presentation, first we start with the role of localization, mainly some introduction concept wise, and after that the some type of levels used for the localization, like beginning level, the level of accuracy. Based on that, we have different types of localization level. Then the basic principle of localization, the basic operation principle, then followed by localization algorithm. What are the existing localization algorithm, mainly in the concept wise, not very technical, but most of the some of the names of localization algorithm and the ideas. Then next is the map generation, then the existing technologies for localization, then some of the implementation, the current work, the current our implementation, mainly PCD map generation, localization result, localization and perception, a combined hybrid system. Also, finally I conclude the presentation. So when we start with the localization, mainly the autonomous driving system, we have 4 subdivision. So the system starts with the perception part, then localization part, then path planning, then control. So in this presentation, mainly our focus is localization. So what is the main role of localization, why we need localization? So when we start with an autonomous vehicle, so the first stage is perception. In the perception, we mainly consider detection of road, signs, lights, objects. So mainly object detection and detection of vehicles, obstacle, objects. So the basic key idea of perception part is understanding the world. So when an object is detected or road or the environment understood to the system, the next stage is localization. So in the localization, mainly where we are, so we identify the vehicle position in relative coordinates, or like in the map coordinates. So based on where the vehicle is located, so based on this result, after localization we plan, like path planning. So mainly calculating the trajectory, so the vehicle knows where it is located. Then next is which route they can go. So they just decided the shortest path to reach their destination. Then after path planning, control. So next last stage is the control system. So in control system, following the calculated trajectory. So this is the basic framework of a autonomous driving system. And in this presentation, mainly we talk about localization, the role of localization, level of localization, how the localization works, and some of our implementation. So mainly localization level. So when we start with the localization level, the first thought is about what road. So we are in the which road. Then in when we consider in the road, which lane. So in lane, where in the lane. So these are like some basic concept of localization level. So the most common approach is using GPS signal. So that is the most common and popular method we used for the localization, using GPS signal from the satellite. But when we consider the tall building or the trees or some type of urban areas, the locating vehicle position is challenging, and the GPS signals easily blocked. So the signal strength is very low, weak. So it's very difficult to identify the vehicle position in that scenario. So in that consideration, we have to think what are the other possible way of locating the vehicle. So the most common, or the key idea is to use the some of the sensors. So the most popular is using lidar sensor or IMU sensor. Even some type of system use camera. So when we consider, we have mainly absolute positioning or relative positioning. We can talk more about what it's exactly mean. So in the absolute positioning, mainly we say about the digital maps. So the concept of maps come, and we create the map. From the map, where is the vehicle is located. So mainly we also use the help of augmented GNSS system. Then in the case of relative positioning, we consider so much sensors, mainly radar or lidar or camera or ultrasonics or inertial motion, like mainly IMU sensor. So just before we discuss about the challenges of GPS based localization system. So if some in some places we have GPS jammer or some type of tall building or trees, the GPS signal easily blocked, and it's very we can the system lose their localization performance or accuracy at some point. So next is how the vehicle localization works, of the basic principle. So mainly when we consider the vehicle location, mainly we have the localization relative to map, or relative location with respect to the last known position, or the feature based localization or satellite based localization. So the main challenging for the localization is the coordinate conversion. So we need to know where what type of localization we use. So the location in the sensor frame, or location in the map frame, or location in the well frame. So that is like main challenge for locating the vehicle position. So some concept of vehicle localization, mainly we identify the ego vehicle position in the map. So for that, most of the system we use GPS or IMU signal, cameras, and lidar and radar signal also. So localization algorithm. So to identify the vehicle position, the most of the system we implement some of the localization algorithm. Mainly the data used for these algorithms are mainly data from IMU, or the speed, acceleration or velocity information, and landmark information, GPS data. So some of the algorithms we use odometry, Kalman filter, or particle filter, or SLAM based approach. So most of these algorithm we start with the initialization, prediction, update, and sampling. So these are like Kalman filter stages. Then map generation. So if even if we have the localization algorithm, we have to balance with where the vehicle is located inside a map. So when we start with the map, we can consider the evaluation of maps. So we started like we paper maps, then digital map or HD map. So in the case of paper maps, like require physical space and can be accessed and used offline only. So mostly use symbols to represent features. But when it comes to digital maps, require digital storage space, can be accessed online. So show all features including estimated travel time, information on traffic, and the actual assets. So no limit to specific areas, and good at showing area overlay from various angles. So when in HD map, so most of these current system or the current autonomous driving system companies, they are focusing on HD map. So creating an HD map is the hot topic for the researchers, and they are trying to address the challenges for creating HD map. So mainly built for self-driving cars. So have extremely high resolution with the centimeter level accuracy, provide virtual assistance, can be easily updated on a daily basis, or provide precise information about ground truth. So when we consider like in the stages of map, like navigation, so driver assistant and automatic driving. So in the case of navigation, standard navigation maps we use, or map attributes used for drivers only, traffic alert, or annual map update. In the driver assistance stage, like standard navigation map with the advanced driver assistance systems attributes, online traffic alerts, frequent map updates. And automatic driving, when it comes up to date information about speed limits, high reliability of dedicated autonomous driving systems attributes, and lane accurate positioning and localization. So based on the map quality, or the information included in the maps, we can differentiate the level of localization, or like navigation, or the level of autonomous driving system. So when we consider the existing technologies for autonomous driving vehicle localization, so the very common method is absolute positioning sensors. Then the main problem is the accuracy is very low, and the computational requirement is lowest. But as compared to the other methods like odometry or dead rocking, GPS IME fusion, or SLAM, these absolute positioning based localization is like not a robust method for the vehicle localization. So our focus is mainly a priori map based approach, so mainly landmark search or point cloud matching. So my research mainly we focus on point cloud matching based system. So the most advantage is highest accuracy. We don't want to compromise anything for the accuracy. Also we have high computational server computers, so we don't want to worry about the computational requirement. We have the resources, so we mainly focus on the point cloud matching based localization. So main challenges: real-time implementation, then the centimeter level localization accuracy. Also, if we have multiple cameras or lidars or combining sensor data, mainly we call it sensor fusion. So mainly in the HD map generation, we focus on lidar-based map generation, camera-based map generation. The localization using GPS, IMU, lidar, and camera. These are the main sensors involved for the localization, and sensor fusion-based localization. So the goals for our implementation was reduce the computational complexity, reduce the system cost, and localization error between the 5 to 10 centimeter. But our current implementation, we reached around 20 centimeter of localization accuracy. So here is the implementation. So we have our test vehicle, and we configure our sensor, lidar sensor, in the top of the vehicle. So then our project goal was to identify, do the localization, not only localization, self-driving in autonomous, like parking, student parking load. We do the self-driving experiment. So that was our goal. So we have here the last three figures shows our driving test environment, and here is the real-time vehicle localization result. So to start with the localization, like first stage is like a matching process. So we have the data from lidar sensor, so we collected the data. Then the next is like mapping process. So we use the NTT based mapping, NTT algorithm, for the mapping. So here is a video demonstration of mapping process. So first we do the trial run of our vehicle in the experiment area, and the lidar captures all scene information, and we create the database. So from this lidar mapping, the next is the PCD map generation. So when the NDT based matching algorithm finish, we have the PCD map, point cloud map. So we use this as our basic map. Then the next time when we do the real time, we do the real localization in this map. So here is the map visualization, PCD map visualization. So then next is our real-time localization result. So in the student parking load, we did our experiment, so and we are tracking the vehicle position. So there are so many challenges we need to address, but currently there is around 20 millisecond, between 20 to 30 millisecond of processing delay in the server side. But still, most of this system works like a reasonable, around 20 to 30 centimeter of localization accuracy. So our goal was to do the self-driving in the automatic car, car parking. So student park loading was our experiment area. Then we were locating the vehicle position. So next is like combine this localization results with the perception part. So that is like our the integration system part. So my colleagues, like the localization part I was doing, and my colleagues, he was working on the object detection. Then we combine the localization and perception part together, like the entire system integration. So the we simultaneously we locate the vehicle position, and also the pedestrian, bicycle, or the object, like in the object detection mainly we focus on the vehicle, cars, and the pedestrian, or also the bicycle. So this type of mainly our pre-trained model is mainly based on this information only. So in these results, we have so many challenges, like sometimes of this object detection algorithm, it's not properly identify the shape of the object. So it's not very accurate system, but our current goal is to improve the performance by introducing some type of deep learning techniques. So in the summary, mainly our goal is to locate the vehicle position and helps the path planning and control of the vehicle. So the most common sensors used in the autonomous driving systems are GNSS receiver, wheel encoder, IMU sensor, LiDAR, camera, and also we have the map. So the map we use as a local map acquisition, and our focus is mainly based on map based localization, point cloud matching. And in the lidar and camera, in the until current experiments, we didn't consider the camera based system, but to improve the performance, mainly most of the systems they consider lidar and camera together, like a sensor fusion based system. So mainly it's involved downsampling, concatenation, region of interest, feature extraction, this type of processing the data. Then the map based localization algorithm mainly use the map information and lidar data or camera data together. And to get the accurate information, like the positioning, accurate positioning, we also consider the data from IME sensor and wheel encoder. So we use the vehicle speed estimation and bias estimation and dead rocking. So dead rocking algorithm, then we use the fusion based localization, mainly involve extended Kalman filter or unsen Kalman filter or particle filter or deep learning base, just like a concept wise, but until now it's no one, I mean the system implementation is very difficult. Then also for the ground truth analysis, mainly we need to consider the GNSS based localization. So the main challenges mainly when the vehicle is in the underground car parking or a tunnels or something. In that time we cannot depend on the GNSS data, so the system completely depends on the lidar based localization. And in the outside like not a covered with the buildings or trees, the GPS data is very accurate. So, but the combination of GPS data, LiDAR data, and the IMU sensor or camera together obtain the vehicle localization. So that is the key idea of localization. Also we use the maps, surrounding map. So use the vehicle location information plus map information together to identify the local vehicle position, then use this result for path planning and control. So thank you.